So before going to next result, I have one point in my mind so that we discussed in the previous lecture. Now, in the previous lecture, we use this TPNK approaches to Q, and it implies this T bar PNK is also approaches to Q. Clear? Here it is T bar PNK. Here is it is TPNK. So some student must have a question why they are the same. Clear? So some must understand, but some have some question in their mind. So these are same because of the definition of extension. When we extend any transformation or function from lower set to upper set, then that function have same value at lower set. Clear? So this PNK and this PNK, it belongs to capital N. So this is extension of T. This is a bounded extension of T. It means this have same values. This have same values. These have same values because of PNK belongs to N. If PNK belongs to N, then by extension, because it is extension of T, then this and that function is same. That's why this approaches to 0. Clear? So it was in my mind to discuss that point. Now, next result is if T from X to Y be a linear operator, right? This is operator mean linear transformation. X is a norm space, Y is again a norm space. X and Y are norm space. So remember these things. These are normed or banal. So these are norm space. If this operator is compact, then its operator is compact. Then its adjoint. Its adjoint is T star. That will be from Y star to Y X star. Y star is dual space of Y and X star is dual space of X. This adjoint is also compact linear operator. So what we are going to discuss? We are going to discuss in this theorem कि every adjoint of every compact linear operator is again compact. Clear? So in simple way, what is the statement and what is the uh, things to remember? What is the point to remember? The adjoint of every compact operator is again compact. Clear? So that is our basic result, and it is started from T is started from X to Y, and T star is from Y star to X star. Y star is dual space of Y, and X star is dual space of X. Right? So this is a dual space of X. Now, given part, this T from X to Y, it is a compact linear operator. Right? Now remember two definition of compact linear operator. First, if we have bounded set in X, then its image is relatively compact. Number one. Number two, if we have bounded sequence in X, then its image has convergent subsequence. So we can choose any of the definition as per our comfort. So I take this because we want this operator from Y star. Clear? So it means our purpose is to find vector from this Y star. Y star, it is a dual space of Y. Dual space of Y mean it is a bounded functional. So this is a bounded functional. If bounded functional, so I consider a set A, F belongs to Y star, such that a norm of F less than equal to C. Why this is norm of f less than equal to c? Because it is a bounded function, or where c is a constant. So I take this A, which is belongs to subset of y star, right? So my aim is to prove that T star from y star to x star is compact linear operator. So our purpose is first take this bounded set in y star, then its image has convergent subsequence. This image is relatively compact. Now this I take this A from y star, and this is a bounded set. Now what is my purpose? My purpose is it's T star A is relatively compact. We already know that. We already know that relatively compact and totally bounded are the same when space is complete metric space. Otherwise not. Clear? Now, in this case, T star A, so this should be in X star. This should be X star. We know that the dual space is finite dimensional, and every finite dimensional are complete, right? So this space is complete. So in this space, totally bounded and relatively compact are same. If set is totally bounded, then it is a relatively compact. If set is relatively compact, then it is a totally bounded. So in order to prove it is a relatively compact, we can also prove that it is a totally bounded. So because of a complete metric space, it will be relatively compact, right? Now our purpose is to prove this is a totally bounded. If we want to prove that it is a totally bounded, the simple procedure is if this set is contained in finite open ball. Clear? So that is simple. What is how we can prove totally bounded? If this is has finite epsilon net, yeah, this is contained in a finite open ball. That's all. Now to prove this, now T we know that is a compact, then image of Tu is relatively compact for every bounded, so that is a definition. Clear? So we take some U operator, U values, norm of x less than 1. So this is a bounded set in x. Because of compactness of T, its image is relatively compact. So this is true in the first step. A relatively compact are totally bounded. So that this it means T of E is totally bounded. If T of U is totally bounded, then it has finite epsilon net for TU. Clear? Yeah, we can say that it is contained in finite open ball. Remember in simple way. It is contained in final open ball with center is y1, y2 and yn. Clear? So we take epsilon which is as per our requirement. So I think our requirement is epsilon by 4c or 3c. So here take epsilon is epsilon by 4c. So by definition of totally bounded, so this Tu is contained in finite open ball, right? So these y1, y2, yn, this is a epsilon net, and it belongs to T of U. It also belongs to T of U. Also, yi belongs to T of U. So by definition, yi can be written as T of xi, where xi belongs to U. Clear? So for every x belongs to U, T of x belongs to T of U. If T of x belongs to T of U, T of U is a part of this, then that member belongs to this unit. If this union, then it belongs to at least one of the bar because it is union. So Tx belongs to Byi epsilon 1 for some I. Remember this, not for all, because it is a union. For union, for some, and for intersection, it is for all. So this belongs to this wall for some I. So remember this thing, this Tx belongs to this wall for some I. Now, it means the difference between these two vectors is less than epsilon 1. So it satisfies this condition for some I. So remember this condition is for some I. This is a 3, condition number 3. Now substitute the value of yi, which is dxi. So this condition is also equation number 4 that will be used later on, right? Now we define a some linear operator P from y star to r raised to power n. It is n Euclidean space which contained n vector from real number. So how we can write that? Here y star, it contains functional. So this is f. So P of f. Now this Rn, this is this functional f take element to R. It means f of any vector which belongs to R. F of any vector belongs to R. F of any vector belongs to R. Because we have n vectors, tx1, tx2, txn. These n vector are nothing. It is a y1, y2, yn. So these are basically that vector. So this is clearly this function is this p is f is a son. We know that f belongs to y star. So f is a bounded linear function. Now since t is relatively compact, so t is a compact operator. So this values. So just remember that this p is a totally bounded operator. This P is a totally bounded operator. Why P is a totally bounded operator? Because this T is a compact, that is given. T is compact operator. So if T is compact, so it is also relatively compact. If T is compact operator, right? So its image, so compact operator, if it is a compact operator, then P is a totally bounded operator. Also dimension of P y star, because that is in, remember, its image is R. What is its dimension? Its dimension is n. So it is a finite. Now, this is a totally bounded as well as it is a less than infinity. So this is a P of this P of any values, P of that set is a that is totally bounded, and this dimension of Py dash star is less than infinity, and it implies P is a compact operator. So this is because it satisfies both the condition. So what is our purpose? Our purpose is to show that this P is this P is this P is compact operator. So we will prove if P is a bounded, a totally bounded operator and its dimension is less than infinity, that is trivial. There is no need of these two results. P is a totally bounded operator, remember this, and dimension is less than 1, then P is a compact operator. So that is trivial result that we will not prove in this part. Now, next is, since A is bounded in Y star, so P of A is relatively compact. Why? Because P is a compact operator. If it is relatively compact, then P of A is totally bounded because relatively compact are totally bounded. Then it has finite epsilon net. So we take that final epsilon net Pf1, Pf2 and Pfn, and epsilon to choose as epsilon by 4. Again, this P of A, this is contained in these finite union of open sphere. Here we take 1, 2, 3 and up to m, because in previous part we take 1 to n. So here we take 1 to m. Yeah, that should be different. Now, for every f belongs to A. Clear? For every f belongs to A, then its image under f belongs to this set. And this set is part of this balls on similar line. So it contains in for some k in one ball. If it belongs to any one ball, so PF belongs to PFK comma epsilon by epsilon 2 for some k. So it satisfies the difference between these two vector is less than epsilon 2. Clear? So this is, so here we used norm or R. So these are a norm different. So this is in R. Clear? So this is equation number 6. Our claim to prove that T of A has epsilon net. So that we will prove this T star F1, T star F2, and T star Fm. This is epsilon net for TA. Clear? Now, we know that what is T. So just remind it. T is operator from X to Y. Clear? T is operator from X to Y. So this is some T operator from X to Y. What is T star? T star is Y star to X star. And this P is from Y star to Rn. This is compact linear operator. So our purpose is to prove T star is compact linear operator. Clear? So that is from Y star. One map goes to in this way and second map goes to in this way. Clear? So this should be remembered. It is also way to find it. Now this PF minus PFK norm square. This is equal to summation of f of tx, fk, txk. Because here we are using the definition and definition of norm. What is PF? It is in n dimension. What is ft1x, ft2x, and so on. And similarly, what is this? It is a fk t1x, fk tx2, and so on. Then we are taking norm that is in term of summation. So remember the norm in r raised to power n. So that is a scaling, and then taking square root of the sum of the squares. Clear? So this is this square is first term square plus second term square plus third term square plus n term square. Then taking then square root of that total values. So it means its square is equal to this form. Clear? So here we are using two definition. One is definition of PF and PFK. Second is norm. That is converted into this form. Right? So do it by your own hand, on pen and paper. Then you will understand in better way. Now this mission, it is a one part. And this is a total sum up to n terms. Then we know that the total sum is always greater than equal to one term, because when the all terms are positive, then sum of n positive term is greater than any one of them. So this value is equal to this, and this is less than equal to epsilon by 4 square. Clear? So that is we find here. This is this values by equation number 6. Now from this we get this result. Now it means our purpose is f of txj. This is f of txj minus fk txj taking square root. So this is less than epsilon by 4. And this term is for every j and f belongs to A. So that is equation number 7. Right? Now, by using these three results, how we can use? We take f of tx minus fk tx. This remember, right? Now, first we enter f txj in minus plus f txj. Again, because of this fk, we entered this term minus fk txj and plus fk txj. By using triangle inequality, we got 1, 2, and 3 terms. Again, by using bounded functional in first and third term. So second term will be same. First and third term, it will be norm of f, norm of tx minus txj. Again, this is norm of fk into norm of txj minus tx. This norm is less than c. Why? Because in this that is a bounded. So norm of f less than equal to c. And this is less than equal to epsilon by 4c. Again, this is less than epsilon by 4. And this is c less than c. And this is less than epsilon by 4c. The total term is 3c by 4 less than epsilon. This result is basically this equation number 7. So 7 is used in this part, right? Equation number 7. Now for this part, from this part, one term is tx, the txj. So tx and txj, one term is, this is one term, tx, this is. So fourth part, one term. And second is norm of f should be less than equal to 1. That is norm of f less than equal to c. That is a third part. So this is norm of f less than equal to c. One is using this. Second is using this term, right? This term. Clear? So this term. And third is using again this term. This term. Clear? So in this case, this, and this less than epsilon. What we get? We get f of tx minus fktx. This is less than epsilon, right? Now, by definition of adjoint of t star, f of tx when t is outside, that is converted into t star. So this is a t star fk. So that function ftx, by using the definition of adjoint, this can be written in this way. Clear? So what is norm? Norm is supremum of norm of x less than equal to 1, this values. Now what is this value? This value is less than epsilon. So this is less than epsilon. It means t star f belongs to ball of center this and radius epsilon. Clear? And k is running from 1 to m. Then it means t star f belongs to either first ball, second ball, or mth ball. If it belongs to any one of the ball, then it means this t star f1, t star f2, t star fm is an epsilon net for t star a. Then it means t star a is totally bounded. So which prove our result. So in the next lecture, we will discuss the diameter and the theorems related to diameter. So that we will discuss in the next